Welcome back everyone to our statistics class notes. Now we're at the top of page 99 and we're in section 7.2 where I'm walking you through a set of 3 simulations where I'm trying to get you to get a deep understanding of what's going to be known as the central limit theorem. All right, in our third simulation here, I'm still going to consider a population of 1,000 people, 250 of whom are walkers. So in other words, 25% of the population. My population proportion P equals 0.25 or 25%. But this time I'm not going to take a sample size of 10. I'm going to take a sample size of 100. And again, I'm going to take 10,000 of these samples. So I'm going to take a sample size of 100 and I'm going to compute the proportion of walkers in that sample, p hat. I'm going to plot it down here. And then I'm going to take another sample of size 100, find a sample proportion p hat that are walkers, plot it. And I'm going to do that 10,000 times, of course, with a push of a button using StatCrunch. It can be done pretty quick. And then plot them. And then I'm going to plot all these guys. And now notice we have a really beautiful unimodal symmetric. Looks just like the normal distribution, doesn't it? And notice that the mean is centered right there at the true population proportion P, which is 25%. So it's looking really good. And what do I notice? It's unimodal symmetric. And it has a lot less variation. I didn't see any guys out here at 60, 70, 80%, right? I don't even see much down here, 0. It's really squeezed in there around the 25%, around the population proportion of 25%. The vast majority are doing a really good job getting close to 25%. All right, so it's very accurate still, right? Most of them are right there at 25%, the bullseye. And it's also more precise. There's not as much spread here away from 25%. So the estimation method remains unbiased. The center is still at 25%, the actual population proportion P. The shape of the histogram looks more symmetric than the one for samples of size 10. And the estimator is more precise because it uses a larger sample size. That's the important thing to remember. The larger sample size we use, the more precise our estimate will be. The standard error is smaller than for samples of size 10. I haven't even talked to you about how to compute the standard error, but remember the standard error is the standard deviation of the sampling distribution. So it's the standard deviation of this. And this has a smaller standard deviation, which you can see. So that means the standard error is smaller than what we saw for samples of size 10.